Hello everyone, welcome back, and in this video we will talk about the PLC local data stack of a Siemens PLC. Let's see for starters in which part of the memory the PLC local data stack lies. Now if we go back to the memory concept of a Siemens PLC, we will see that the local data stack exists inside the data work memory section. We know that the work memory is divided into two parts: the code work memory and the data work memory. The code work memory has the program, the process image of inputs and outputs, and the diagnostics buffer data. The data work memory has all of the data blocks and also has the local data stack, which we will be talking about in this video. So basically, we know that the local data stack is a memory area inside the data work memory of the PLC. And then this local data stack is then divided into multiple areas. Each of them is called a priority class. And each of these classes is assigned to an organization block and function blocks and functions that run under it. So basically in your program, if you're inside of OB1, which is the main organization block where we put most of our code, and you want to assign some local data to OB1 itself for any function or any function block that is called under it, the local memory for this data will be assigned from the subarea assigned to the priority class number 1 inside the local data stack. So that's what we need to know about the local data stack. Now, why is local data actually useful? We will know later that local data can be assigned, then freed, then reassigned again. So if there is some sort of data that is only used locally for your block and is not needed to be retained for the cycle, it's better to use local memory for this type of data, for it doesn't use permanent space inside your work memory. So, that's the case for which we use local variables instead of placing the data later inside a data block. Now let's see an example where we will explain the local data stack and see what happens if we try exceed the space we assign to priority class number 1 by the code that is actually running inside OB1. So let's see that example. So first we will create a new project, and before we proceed with the example, we first need to do the hardware configuration. First we need to create an S7400 station and do the hardware configuration for that station. The first thing we need to do is to add a rack. And let's say we will choose CR3 as our rack. Then we need to add a power supply to the first two slots of CR3, and let's say we will add the first standard power supply we meet here. After that, we are ready to add our CPU to the configuration at slot number 3, and then we'll choose the CPU just because it has a Profinet interface. And we will leave the IP settings and the subnet mask as they are. Let's also create our first Ethernet bus and call it plant bus. And now that we have inserted our CPU, we have finished our hardware configuration. Now what we need to do is to start the simulation. So we go back to the Simatic Manager and click Start Simulation from the toolbar. Now inside the simulation we need to make sure that the PLC is in stop mode before we download anything to it. And when we put it in stop mode, we can actually download our hardware configuration to the simulator. And as you can see, this here is the same IP address of the CPU. So now let's download it. And as you can see, it was downloaded without errors. So before we leave our hardware configuration, we need to look at the local data stack in the properties of the CPU. So let's open the properties of the CPU by double tapping it, and let's go to the Memory tab. And as you can see here, the size of the local stack is basically the maximum value shown here. And as we said before, the data stack is divided into multiple priority classes. So these entries represent each priority class and how many bytes they have. So basically, the entire local data stack occupies 8,192 bytes inside the work memory of the PLC. And it is divided into priority classes, each having a certain amount of bytes. Now for our example, we will be concerned with priority class number 1, as we will write our code inside OB1. We will actually show that if your code assigns more local variables than this 758-byte area can handle, you will actually get an overflow error and the PLC will go back to stop mode because of that. Now we will close our hardware configuration and we will start coding our example. Going back to Simatic Manager, and under our Simatic S400 station we have our CPU. And inside that CPU a program was created by default, called S7 program. Now if we go inside the blocks, we will see that we already have OB1 by default. We will first create two other functions that will be used in our example. So first we will add the function FC1. And then we will add the second function FC2. Now, let's take a look inside OB1. You will find your local data inside the interface of the block under the Temporary tab. So looking inside a Temporary tab, you can see that we already have some variables here by default. To see how many bytes these variables take, let's create a byte variable after them and call it variable1, and then see its offset address. And as you can see here, the offset address for the variable is 20.0. And so we can say that OB1 requires by default 20 bytes of local memory inside priority class number 1. These 20 bytes are necessary for its operation, and it can't operate without them. And you can add your local variables or temporary variables after these 20 bytes. But for now, let's remove the one variable we added. Now, let's go inside FC1. And under the Temporary tab here, we will add 3-byte variables. Let's call them variable 1 to variable 3. And let's save that function and download it. Now let's go to our second function. And under the Temporary tab here, we will add only 1-byte variable. Let's call it variable 1. And let's save that function and also download it to the PLC. Now we go back to OB1 and we will call our two functions using the unconditional call command. So we have unconditional call FC1 and unconditional call FC2. So let's save OB1 and also download it to the PLC. Now that we have finished programming our example, let's say that you want to know how much local memory you used in your program. The Simatic Manager has a very interesting tool for handling the occupation of all the PLC resources. And this tool is called Reference Data, so let's have a quick look at it. So you should go to Options, Reference Data, and click Display. For local memory, we are only concerned with the program structural section, which actually lists the tree diagram of the program blocks and local memory occupied by each block. So in the first tab we have all of our blocks. And we are interested in these two tabs: local data for block and local data for paths. So let's first look at the first tab, which is local data for block. First we have OB1 and it has 20 bytes. Remember that OB1 had those 20 bytes by default for its operation. And then if we look at function 1, we will see that we have 4 bytes. But we previously created only 3 local byte variables, so why do we have 4 instead of 3 here? To understand that, let's go back to function 1 and let's first remove variable 3 and save the program again. Now if we look back at the reference data, and for function 1 we only have now 2 bytes of data for our 2 variables. So what you should know now is that local memory is assigned on word basis and not byte basis. Now let's go back to our 3 variables. And we should actually be back at 4 because the system had to use an entire new word to assign variable 3, which takes only half of it. And now if we add a 4th variable, what you expect to see in the reference data is also 4 bytes. And that's what happens here. This also applies to function 2, which had only 1 byte variable. As you can see here, the block is using 1 word or 2 bytes from the local data stack. And that's it for this tab. Now let's talk about the second tab, which is local data in paths. This tab actually shows how space in the local data stack is assigned, then released, then reassigned again. So if we look here first, we had OB1, which actually will always be occupying 20 bytes of data. But then OB1 calls the function FC1, which requires 4 bytes. And because the function FC1 was called under OB1, we have 24 bits required by this path when the function FC1 starts. However, after the function FC1 is executed, the 4 bytes required by FC1 are released again. So we are back again at 20 bytes. Then OB1 calls the second function FC2, which requires only 2 bytes of local memory. And after the function FC2 is executed, these 2 bytes are also released. So again we are back at 20 bytes until OB1 is finally finished. And that's actually what happens in one cycle of the program. So this behavior will repeat for every cycle of the program. Now this means that from this second tab, if a path requires memory greater than what we configured in the hardware configuration, you should get an error indicating that the PLC can't assign that memory. And therefore, we care mostly about the maximum number in that column. And that is what we will see in the next example. Looking back at the hardware configuration, we had 758 bytes available for priority class number 1. So let's just occupy that space completely and then see what will happen if we try to exceed that space. So because we know OB1 has to occupy 20 bytes of data, we will just need to add 738 bytes to our first function FC1. And now if we look at the reference data, we should actually be at 758 in that path. And let's first download that to the PLC. And push it back to run mode. And as you can see here, the PLC stays at run mode with no errors. Now let's try to exceed the 758 bytes. So we just add one more variable to the function FC1. And now if we look at the reference data, we have 760 in that path. And let's download that to the PLC. And then push it back to run mode. And as you can see here, the PLC returns back to stop mode with the system fault LED getting activated. And now let's go to our diagnostics buffer and see what happened there. We do that by going back to Simatic Manager, right-clicking the CPU and choosing Module Information. Then we go to the Diagnostics Buffer tab. So what is happening? Well, starting from entry 7. First here we had our startup information from the previous time we pushed the stop button. And when we pushed the run button, the PLC transitioned first from stop mode to startup mode and called first the warm restart organization block OB100. After that, the PLC changed from startup to run mode. And when it changes to run mode, OB1 was called, which then called the function FC1. And here the PLC failed to assign local memory for FC1 and gave us that error saying that it failed to allocate local memory. Then the mode transition back to stop mode happens. And finally, the startup information is updated for the next time you'd start the PLC. Now if we go back to 758 bytes, and try to run the PLC again, we will see that in the diagnostics buffer it will run without error and it won't go back to stop mode. So that concludes our discussion about the local data stack. And this is the end of our video. In the next video we will discuss another memory area of the PLC called the process image of inputs and outputs, so stay tuned and please like, comment and subscribe to the channel.